Okay, so let's start. In the last few classes, we've been looking at support vector machines, which are essentially linear classifiers with some specified margin constraint. Right. So the hard SVM was basically an empirical risk minimizer for the case where you have a linearly separable data set, but it is that empirical risk minimizer that maximizes the margin. All right. In the case where the data set is not linearly separable, we don't have an efficient way of finding the ERM. But then support this soft SVM algorithm, which is basically obtained by using the same intuition that we had for the hard SVM problem. This gives a reasonably good solution, even though it is not it's not an empirical risk minimizer. And but in particular, for the soft SVM algorithm, we can also derive generalization error bounds. And in both cases, for the hard SVM and soft SVM, we can use a stochastic gradient descent algorithm to solve for the or obtain the support vector machine classifier. Right. So all of this works reasonably well when the data set is actually linearly separable. But in most cases, if it's linearly separable or approximately linearly separable, because in the end, either the hard SVM algorithm or the soft SVM algorithm, they can't do any better than the best possible linear classifier. Because we remember that the generalization error or the excess generalization error or the excess risk consists of two terms, an approximation error and an estimation error. Right. And there's a trade-off between the two. If you choose a very rich class, then again one of the terms is going to increase. If the class is not too rich, then again you may get a small estimation error but a poor approximation error. Right. So there is always this trade-off between the approximation error and estimation error. So we want to go beyond support vector machines because most of the data sets that we see, even simple looking data sets, may not be linearly separable. Right. So let's start with a simple example. Let's take the case where x is equal to r. The domain is the set of reals. All right. And the data generating distribution is, or if you want, let's take a subset of this. Let's take x equal to the interval between 0 to 1. And let us suppose that the true classifier or y indicator that x lies between some a and b. Right. So we see some bunch of points. The brown points are labeled 1 and the red points are labeled 0. So maybe this is the interval from 0 to 1. Okay. What would a linear classifier do? What does a linear classifier in R look like? Yeah? Can you be a little more precise? No, my question is what is a linear classifier in one dimension? A point, or it's a threshold classifier, right? But it's a threshold classifier where you have either set of all h such that h of x is indicator x less than or equal to alpha, or indicator x greater than or equal to alpha. Say strictly greater than alpha and strictly less than alpha. This is what any linear classifier can look like. Right. So here's a homework problem. Suppose that Px is the uniform distribution over 0 to 1, and let's fix a particular ground truth. Let's say that y is indicator that x is between 1/4 and 3/4. Show that for any h, or let me ask the following way, find a lower bound on R of h. In particular, I want you to show that the generalization error for any linear classifier is lower bounded by a constant. So no matter how many additional samples you get, the generalization error can never be driven down to 0. So this is the case even though there is a simple classifier, a non-linear classifier, that actually achieves 0 generalization error, right? So the natural idea would be, let's try to enhance the hypothesis class that we're looking at. Instead of looking at just linear classifiers, maybe we should look at non-linear classifiers as well. But the advantage of linear classifiers, in particular support vector machines, is that they also come with an efficient algorithm to find or to learn a classifier, which may not be the case for much more general non-linear classifiers. And in particular, for a different hypothesis class, let's say in this case I have a hypothesis class with 2 thresholds, and maybe I want to look at, let's say, polynomial classifiers and so on, right? You can try to look at a rich class of non-linear classifiers, but in each case I would have to either find the empirical risk minimizer through an efficient algorithm. I have to design a different efficient algorithm for either finding the empirical risk minimizer or approximating the empirical risk minimizer, which could be difficult to do. Right? And in addition, I also want the feature that I should be able to derive bounds on the generalization error for this rich enough class. All right. So then, is there a natural way of extending the ideas that we've already developed, the tools that we've already developed for support vector machines, to go beyond just linear classification? And one such way, the approach that we will take is that of finding an embedding from the space from the domain into a much higher dimensional space. All right. So you embed into a higher dimensional space and you look for a linear classifier in the higher dimensional space. Better than 1 by 4. How do you achieve 1 by 4?
Choosing 1 by 4 or 3 by 4 as the threshold.
Okay, but how do you say that the probability of error is only 1 by 4?
If the x belongs to the interval 0 to 1 by 4,
Correct.
it's probably classified.
Correct.
So that's probability of error is 1 by 4.
Correct.
So can you do better than that?
You can't. But you have to prove that you can't do better than that. Okay. So the idea is to embed into a higher dimensional space. Specifically, you look for a map from X to some higher dimensional space, let's say X prime, and then look for, find, let's say, an SVM over X prime. All right. And why can this potentially, why can we even hope for this to work? Let's go back to the previous example and we look at the following embedding, which is, so let's take an even simpler example perhaps, where X is equal to R and Y takes the form indicator norm X is greater than or equal to alpha, or okay. You can see that essentially the previous example and this can be thought of as equivalent. You just have to shift things around. All right. And if you can solve this, then you can solve the previous problem as well. But just for notational convenience, let's look at this particular ground truth generating distribution. Now in this case, if I take the map from R to R2 defined as psi of x to be equal to x comma x square, right? In this case, this y, this is equivalent to x square less than or equal to 1, right? So which means that this the class of linear classifiers over this, yeah, x square less than or equal to alpha square, yes, right? So the space of linear classifiers over R2 with this particular embedding actually can achieve zero generalization error. So you consider a new hypothesis class, which is right? So once again, we are only looking at linear classifiers. So, but except that I have this embedding first, and then a linear classifier over this higher dimensional space. So just by going from, just by using an additional embedding, I can still use the same tools that I developed for support vector machines to design a non-linear classifier. It doesn't mean that every nonlinear classifier can be generated using this particular approach, but hopefully a rich class of classifiers can be obtained using this new approach that I have. All right, but this doesn't mean that it comes for free. We have to pay something extra in order to do this. All right, because after all, we are embedding points in a higher dimensional space. So that comes with two limitations. Well, since you're going to a higher dimensional space, number one, the dimension increases. That is, the dimension of the ambient space or the domain is now increased, and therefore the VC dimension also increases. Because ultimately the VC dimension of your hypothesis class is D plus 1, where D is the dimension of the domain. Right? So the VC dimension of H prime is going to be the dimension of H prime plus 1.
Dimension usually increases by only one.
No, not necessarily. In this particular example, we increased it by 1, but sometimes you may want to increase it even more. Right? So the VC dimension increases implies that our bounds on the generalization error also become weak. So one solution to this was already seen earlier. That is, instead of the VC dimension, if we have margin-based bounds, then we can obtain better bounds on the generalization error. So in other words, if I have a data set and it is linearly separable over some higher dimensional embedded space, then the margin, the guaranteed margin also gives me a bound on the generalization error. Okay, so this works only if there is a non-trivial margin in the space into which this is embedded. All right. So just on the point, so the space into which this is embedded will be called the feature space. So if the data set is linearly separable in the feature space, then I can use a margin-based bound to derive an upper bound on the generalization error. So that takes care of one thing. The second issue is that since the dimension increases, the computational complexity also increases. Right? Because the computational complexity depends on two things. One, the dimension of the ambient space. The way we posed the support vector machine optimization problem, it depends on two things. One, the dimension of the ambient space. The second is the number of data points, because the number of data points will kind of give the number of constraints. Or if you're using stochastic gradient descent, then again, it depends on the number of points that you have. The second is it also depends on the dimension, because you have to compute a gradient at each step, and the gradient, the complexity of computing the gradient is proportional to the dimension. All right? And we'll see that the second issue will not really become much of a problem. we'll use the kernel trick. In particular, we'll want to design algorithms that scale with the number of data points, but do not scale with the dimension of the feature space. All right. So that's one thing, and this approach of embedding points in some high dimensional vector space also will give another advantage, because suppose that the domain is not RD. So far we were assuming, in order to design the linear classifier, we were assuming that the data comes from RD. But that's not true in practice, right? Because sometimes, let's say you have a text document. You need a way of embedding these text documents into some real space, right? So you need to find an embedding in the first place. And these kernel methods, as we'll see, will also help us design such embeddings. All right. Before we proceed, we'll need some kind of a structure on the feature space. So we'll demand that the feature space is what is called a Hilbert space. So it's not any arbitrary vector space. In general, it may not, if it's R to the d prime for some d prime, then that's also already a Hilbert space. But more generally, it can be even an infinite dimensional space, not necessarily finite dimensional. So what is a Hilbert space? Any complete vector space. For now, we'll assume vector spaces over R. So when I say a vector space over R, it means that the underlying field is R. So all linear combinations are real linear combinations of vectors. With an inner product. What is a complete space? It means that all Cauchy sequences that is so if you have a sequence of elements such that xn minus xm tends to 0 as n comma m tend to infinity, so any sequence which satisfies this property is called a Cauchy sequence, and the space is said to be complete if every Cauchy sequence has a limit. All right. So for example, if you take, say, an open interval, right? If this is my space, let us say, then not every Cauchy sequence has a limit, because you can take a sequence that is converging to the end point, right? So which means that it does not converge to a point in your space, but then it is a Cauchy sequence because successive elements are getting closer and closer to each other. Right? So the space is complete if this happens. Or another space to consider is, let's say, the space of rational numbers. You can always take a sequence of points that converges to an irrational number. This is also a Cauchy sequence. Any sequence that converges to an irrational number is also a Cauchy sequence. But then it does not converge to a point in the space of rational numbers. And similarly, what is an inner product? An inner product is some map. Let me use simple notation. Let's say f from if it satisfies the following three properties. One is that f of x comma x is greater than or equal to 0 for all x, and equality holds if and only if x is the 0 vector. So here we are assuming that x is some arbitrary vector space over R. Okay, no other assumption. It could be finite dimensional, it could be infinite dimensional. The second is that it should be symmetric. F of x comma y should be equal to f of y comma x for all x comma y, all vectors x comma y. And the third property maybe one more, alpha x comma y should be equal to right. So let's take the space to be RD. Okay, can you give me some examples of inner products? Dot product is the most common inner product. So this satisfies all of the properties that we have above. let's say that I look at the following inner product, alpha I xi yi, for some fixed constants, or let's just, where alpha I is in R. When can this be an inner product? These alpha i's are fixed, they're independent of x and y. Okay. What happens if one of them is negative? Correct. So basically, if any of the alpha i's is negative, and you choose the vector x to be all zeros except you take it to be the ith standard basis vector, then the inner product between x and itself is going to be negative, right? Should alpha i's be strictly positive, or is it enough for it to be non-negative? Why? Correct. When x, you should not, if x is non-zero, then you don't want the inner product to ever be equal to 0. Between x and itself to be ever equal to 0. So it should be set of all positive real numbers. Alright? More generally, so A should be symmetric and positive definite. Yeah, but sometimes that additional qualifier of symmetric is added, so we'll also add it. Right. So we'll always assume that the mapping from when we're looking for an embedding into some feature space x to x prime, we'll assume that x prime is a Hilbert space. Or to be more precise, we look only for those embeddings which map our points to some Hilbert space. But as we've seen previously, one problem is that in all of this, we have to perform computations in this high dimensional Hilbert space in general. Right? And the computational complexity, if we do it naively, then the computational complexity will scale with the dimension of the feature space. And we want to completely avoid that altogether. And that is the main, avoiding that is the main requirement of using these kernel methods. That is, we don't really worry about the embedding itself. Because if you think about it, the algorithms that we had, right, the high level intuition is that if you look at the objective function and as well as some aspects of the algorithms that were used in the hard SVM and soft SVM classifiers, everything just depends on inner products between points. Right? So here the objective function, remember that the classifier is always the form indicator W transpose X is greater than B. Right? So the classifier itself just requires you to be able to compute the inner product. All right? And similarly, the optimization problem itself depends on the norm of W square, which is the inner product of W with itself, and inner products of W with the data points. The soft SVM as well depends on this particular function, the norm of W square, and the inner products between W and Xi. So if we were somehow able to just compute the inner products, then hopefully we don't have to go through the process of mapping X to the high dimensional space through psi, and then computing, solving for the optimizer, and then coming back to the lower dimensional space. All right. So for this, we'll use this notion of a kernel. All right. A kernel K is basically just a map from X cross X to R. So any map is called a kernel, but we'll look for kernels with some nice properties. So in particular, we want the kernel to look like a valid inner product. I can't choose an arbitrary kernel and then hope that there exists such a mapping, or it looks like an inner product in some high dimensional space. So if we have some underlying mapping, so this point is almost trivial. So if psi X to X prime, then this is the sort of kernel that we're looking for, right? But what properties does this kernel have? It inherits all of the properties of the inner product, right? So it has the following properties. So K is symmetric. And the second property is that if I construct a matrix, so you take any set of n points, where n is arbitrary, I construct this n by n matrix of K of x1 comma x1, K of x1 comma xn, K of xn x1, xn xn. So no matter how I choose the points x1 through xn, this matrix is guaranteed to be symmetric and positive definite. Or at least it's guaranteed to be symmetric and positive semi-definite. Because I could potentially choose two different ki's, xi's to be the same, or some of the eigenvalues of this particular matrix could be 0. But this matrix is definitely going to be symmetric, and all of the eigenvalues are going to be non-negative. So we'll say that a kernel is positive definite symmetric. We'll abbreviate that as PDS. if for every collection of points x1 through xn, this particular matrix k of x1 up to k of xn is symmetric positive semi-definite. So this matrix is called a kernel matrix or a gram matrix. So if K has to correspond to an inner product between some psi of xi and psi of xj, then clearly this matrix should be positive semi-definite for every x1 through xn. Right? So remember, at this point, a kernel is an arbitrary function. If the kernel corresponds to an inner product between the embedded points in the feature space, then it's an actual inner product. But by definition, for a kernel, it does not need to correspond to a valid inner product between embedded points in the feature space. Right? So some k the kernel could be an arbitrary mapping. But we want to choose those kernels for which there exists a mapping psi such that this corresponds to an inner product between points in the feature space. Which one? When it's an inner product. So you just consider, so what, let's just take, let's take a 2x2 example perhaps. Right, let's say x1 transpose x1, x1 transpose x2, x2 transpose x1, x2 transpose x2, and let's multiply this beta. What would this give me? Yeah? Alpha square x1 transpose x2 suppose x2 x1. So more generally, if I have, let's say, a vector alpha 1 through alpha n times let's say this inner product matrix alpha n, what can you say? It will be a double summation over I and j, alpha I alpha j, xi transpose xj, right? Which is the same as sum over I, or which yeah, it's equal to it's basically going to be summation over I alpha I xi transpose summation over j alpha j xt. Right, which is going to be non-negative for every alpha I. Note that we can only say that this is non-negative. We can't really say that it's positive all the time because the xi's need not be linearly independent. If they're all linearly independent, then this is going to be greater than 0 for all non-zero alpha or non-zero vectors alpha. But in general, this is just greater than or equal to 0. So a positive definite symmetric kernel is one for which the Gram matrix is always positive, is always symmetric, positive, semi-definite. Questions? Okay. So now, suppose that we've somehow found a kernel that corresponds to an M. So basically the idea is the idea behind kernel methods is find a K that corresponds to some embedding from x to x prime, such that K can be computed efficiently, even if I can't compute psi efficiently. So we don't care even if we have a closed form representation of psi. We'll just try to find K such that K can be K of x1, x2 can be computed efficiently. And we'll see why that is enough. Right now we have some intuition because most of the algorithms just depend on inner products. It's enough, it's hopefully going to be enough to just design your algorithm such that you only need to compute K of x and something else and nothing else. Right. So now, suppose that we can obtain our classifier by solving min over w of some function inner product between w and psi of x1, w psi of x2, psi of xn plus maybe some kind of some function of norm of w. okay, where f is any function from Rn to R, which takes as arguments, which in our case just takes the inner products as arguments. So each of these inner products is a real number. So f is any arbitrary function that takes n real numbers and as output and outputs some real number. I don't demand that f is convex or anything else. Okay, just some function of n real numbers, and but R is non-increasing. Sorry, non-decreasing. Okay, so just to as a sanity check, the soft SVM algorithm, what is R of u? Yeah, lambda or lambda by 2 square. And what is f? So f would correspond to the hinge loss, right, which is 1 over n sum over I max between 0 and 1 minus yi times u. Yi ui. So f is a function of these n inner products, where ui would be the inner product between w and psi of xi. You can do this similarly for the hard SVM problem, except you have to be a little careful in defining f. Okay, so suppose I have the framework that we're operating in is that we can obtain our classifier by solving for an optimization problem that looks like this. All right. Then we have the following so-called representative theorem. Which says that if psi is any mapping from x to x prime, where x prime is a Hilbert space, then there is some set of coefficients alpha 1 through alpha n. Let me call this optimization problem star, such that W star is, or let me say some equal equal to 1 to n alpha I is a solution. So basically this is saying that suppose I want to solve or find the soft SVM solution or hard SVM solution or any such classifier in the feature space, right? Then the solution can always be written as a linear combination of the embeddings of the data points. We saw that that is the case for the support vector machines, right? But what this is saying is that even if we have, even if we embed it in the feature space, then this still holds, which is something that's natural to expect. But remember that we are operating under a more general framework where f is any arbitrary function and r is any non-decreasing function, not just the soft SVM or the hard SVM objective. All right, so let's say that W star is, we'll start with any arbitrary solution for the optimization problem, for the minimization problem. Okay, and let's define W to be the orthogonal projection down to the space that is spanned by the embeddings of psi of x1 through psi of xn. Okay, so for this to exist, the corresponding space x prime should be a Hilbert space. It turns out that completeness is necessary for there to be a unique orthogonal projection. Okay, so this is the space that we are interested in. So this is the orthogonal projection. Therefore, we can write W star as W plus some vector u, where u lies in the orthogonal complement, where the inner product between u and w is equal to 0. Okay, so now what can you say about the norm of W star square? So it's equal to norm of W square plus norm of U square. So what can you say about the relationship between norm of W star and norm of W? So the norm of W star must be greater than or equal to the norm of W. Okay, that's one thing. So which means that R of norm of W star should be greater than or equal to R of norm of W. Okay, so if you just look at the second part of the objective function we are trying to minimize, W has a smaller contribution to the second part compared to W star. Okay. Now let's consider the first term, or let's take the inner product between W star and psi of xi. This is the inner product between W plus U, because W star is W plus U, and psi of xi by the linearity property of inner products. This is equal to the inner product between W and psi of xi plus the inner product between U and psi of xi. But what can you say about the second term? By definition, what is U? Yeah, so U lies in the orthogonal complement of the span of psi of x1 through psi of xn. So the inner product between U and any psi of xi should be equal to 0. So this is equal to the inner product between W and psi of xi. So f of W star psi of x1 up to W star psi of xn, this is equal to f of W inner product with psi of x1 up to inner product between W and psi of xn. So what we've basically shown is that if W star is any vector that minimizes this particular objective function, then there is a W which lies in the span of psi of x1 through psi of xn, which has an object which achieves an objective which is less than or equal to that achieved by W star. Because what is achieved for the first term is the same as what is achieved for W star. So W star and W achieve the same value of f, but W achieves potentially a smaller value of r compared to W star. So this means that W is also a solution of the objective function that we were interested in. Right? So this means that in particular for the soft SVM, for kernel soft SVM, you can express any solution of the embedded soft SVM problem as a linear combination of the embedded data points. All right. So that's one thing, that's finding the solution, finding W. The second is, suppose that we somehow found W. Right? We solved the optimization problem and found W. Then what is h of x going to be equal to? It's basically indicator that the inner product between W and psi of x is greater than or equal to, let me take a step back. All right. So basically this, everything boils down to computing W and psi of xi, which is nothing but the inner product between summation over all j, some alpha j psi of xj and psi of xi, which is summation over all j, alpha j, inner product between psi of xj and psi of xi, which is summation alpha j k of xj comma xi. And the norm of w square is summation over all I, summation over all j, alpha I alpha j, k of xi xj. Right? So basically our optimization problem can be reduced to, so this is equivalent to solving for minimizing overall alpha 1 through alpha n of f of summation over all j, alpha j k of xj x1 summation over all j, alpha j k of xj xn plus r of square root sum over I, sum over j, alpha I alpha j, k of xi xj. So instead of minimizing over w, which was a vector in this high dimensional feature space, so the number of parameters in w depended on the number of dimensions or the size of your feature space. Now I've reduced that to a different optimization problem where the number of parameters is number of data points. So in situations where the dimension of the feature space far exceeds the number of data points that I have available, this becomes a more efficient optimization problem to solve. So in particular, the soft SVM problem would have the following objective: to minimize over vectors alpha of lambda alpha transpose g alpha plus 1 by n summation I equal to 1 to n max between 0 and 1 minus yi times the ith component of the vector g alpha, where G is basically the Gram matrix. right? So even though I'm looking for a non-linear classifier, for example, if you go back to the sort of polynomial classifier that we just designed previously, where you map x to, you embed that into x comma x square, right? That can still be represented as the solution to this, or finding the classifier in the feature space corresponds to finding a solution to this particular optimization problem, which is essentially just a quadratic optimization problem. And I can still use techniques like stochastic gradient descent or any other solver for that matter. And once I find the solution, so let's say that we find that alpha star is a solution, then your h of x can be just represented as indicator summation over j alpha j star k of xj x greater than 0. Because this is exactly indicator inner product between w and psi of x greater than 0. So even prediction just requires you to perform a kernel operation. So throughout I didn't need to compute psi, either for finding the classifier or for prediction. So we completely bypass trying to compute psi, and instead everything boils down to computing k. So if you are able to compute k efficiently, then you can do this entire process that you had for soft SVM. Okay, so in fact, all of this would still work even if we didn't have a closed form expression for psi, or psi were extremely complicated to compute, or even if the dimension, or if psi even embedded vectors into an infinite dimensional space. So then the natural question to ask is, how should we choose k? If we already have a psi, then computing k is natural. But then that process requires us to first compute psi in order to compute k. But we don't want to go through that process, because if we have to first compute psi and then compute k, then you still have the overhead of computing psi, and therefore the complexity of computing k would depend on the dimension of x prime. Right? So we don't want to do that. Can we choose a k that we know works, and there exists a psi such that the mapping is to a Hilbert space? Right? So the answer is you choose k to be a PDS kernel. So the theorem says that if k is PDS, or there exists a psi from x to x prime, which is the Hilbert space, with k of x1, x2 to be the inner product between psi of x1, psi of x2, if and only if k is a PDS kernel. So if k corresponds to valid inner product, then k must be a PDS kernel. We've seen that previously. But if k is a PDS kernel, then it guarantees that there is some embedding into a Hilbert space such that k corresponds to computing just the inner product between feature vectors. All it says is that there exists an embedding. It doesn't give you any closed form expression for the embedding. Okay, so let's start with some examples of PDS kernels. The first example is a polynomial kernel. So here we are assuming that x is some RD, and k of x1, x2 is some constant plus the inner product between x1 and x2 whole to the power k, some little k. For some positive integer k. Okay, so as an exercise, show that for this particular kernel, psi is a map from Rd to Rd plus 1 to the power k. Alright, so it's a much higher dimensional space where the components of psi are indexed by all possible subsets of size at most k, product I in j x3. I'm sorry? Which one? D plus 1, because I can also not choose an element. So J is the set of all subsets. So there are basically k elements. The k can be 1 to 3 up to D, but also it can be, let's say, 0, where 0 means I'm not picking any element. Okay. Okay, so this is particularly for C equal to 1. The constant over here is 1. If it's not equal to 1, then it just amounts to a rescaling. But we'll see a different way of showing that this is actually a PDS kernel. In general, you don't try to find the embedding directly. You try to find, you try to prove separately that it's a PDS kernel. And there are techniques to do that. We'll see that in a while. All right. So maybe before I go to the next example, we'll just see how computing the inner product using the kernel is better than computing the inner product by embedding into the feature space. So if I embedded to the feature space and then computed the inner product, then what would be the complexity? How many operations would I need to do if I had to first embed x1 to the feature space, x2 to the feature space, and then compute the inner product? So complexity would be roughly d plus 1 to the power k. Right? I'd at least need those many operations, because I have at least d plus 1 power k multiplications, because there are d plus 1 to the power k components, and that minus 1 number of additions. Right? So the complexity scales as order of d plus 1 to the power k. But now if I use the kernel to compute the inner product, then the complexity is just d. Right? Because I need to compute the inner product between x1 and x2, which require d multiplications and d minus 1 additions, plus 1 addition, and then I have to raise this to the power k. So the complexity is essentially k times d instead of d to the power k. All right. So obviously doing that is better.
We can also do embedding projection so that it is of same dimension. Input is also d dimension, output is also d dimension.
Then you will not get anything, right? Because if you're embedding to the same dimensional space, then you can't embed a more complex classifier. So the embedding of the classifier would still be linear or almost linear.
Like in that example, we had a label 0, label 1 and label 0 in one dimension, 1D case.
Correct?
If there is, let's say there is some non-linear transformation, so
Uh-huh.
all the ones will come to this side and 0 comes to the other side, still the dimension is same, which is 1.
But then you will need to find a PDS kernel corresponding to this, right? So if you can find such an embedding, that's fine, but in general you won't be able to do that. All right. It's only in a higher dimensional feature space that you will still be able to find a rich enough class of classifiers. All right. In particular, it should not be dependent on the actual realization of the ground truth. It can depend on the class of ground truths, but not on, you will not be able to find one nonlinear map that does this transformation well enough. Right. Just think about it a little. Okay. Maybe this is a good point to stop.